of the Director of Labor Relations. The Rural Route Evaluated Compensation System, RRECS Development and History. David Heather, National Director of Labor Relations. The Rural Route Evaluated Compensation System, RRECS, replaces the current evaluated compensation system with a mostly automated data capture system capable of generating daily counts of work activities, new engineered and statistical standards based on generally accepted industrial engineering principles, and an automated system of business logic that calculates and updates evaluations of rural routes. The RRECS systems enables automation of almost all data capture necessary for accurate engineered route evaluations, which eliminates the need for comprehensive mail counts. RRECS draws on existing data from throughout USPS to count the work activities performed daily by rural carriers. These counts are largely automated and require minimal carrier intervention. The resulting database is used to calculate standard times for the work activities and routes. Count data is also captured from mapping software developed by the project. Mapping customers and routes requires a significant upfront investment, but once they are mapped, future change will be captured in an automated updating process and remapping will be minimal. The mapping system provides an efficient mechanism to digitally capture the door, mail stop, mailbox, and direct door delivery stop associated with each customer address. These mapped locations are used to calculate walking and driving distances. RRECS engineered standards are based on generally accepted industrial engineering practices. They have been validated and are fully documented and available electronically in a uniform structure and format. Systematic procedures for creating, auditing, and changing standards, and resolving standards disputes were provided. A one-of-a-kind drive speed matrix has been generated based on millions of drive time samples. It will calculate accurate drive times based on specific route characteristics. The system software will generate route evaluations and update them as necessary, according to rules to be negotiated by the parties. RRECS provides an accurate and transparent system for enabling changes in engineered standards required by the dynamically changing USPS business environment. Background. The origin of RRECS. The NRLCA and USPS agreed to create the Rural Route Evaluated Compensation System, RRECS, in a Memorandum of Understanding, MOU, appended to the Interest Arbitration Award issued by Neutral Chair Jack Clark on July 3, 2012. The MOU specified the following procedure for selecting a panel to oversee the project. The project will be headed by a 3-member panel. Each party will appoint a member of its choosing, within 30 days of the signing of this Memorandum of Understanding. These individuals shall be professional industrial engineers with relevant experience in sound industrial engineering principles and modern computer technology related to work measurement and delivery route design. Within 60 days thereafter, those 2 members will select and engage the chairperson, who shall be a professional industrial engineer who possesses the same qualifications. In the event the 2 members are unable to agree on a chairperson, a neutral arbitrator who is a member of the National Academy of Arbitrators will decide who will be the chairperson. The NRLCA appointed Ken Maracle, Professor Emeritus, University of Wisconsin Extension, School for Workers, as its representative in August 2012, and USPS appointed Don Ratliff, Professor Emeritus of Industrial Engineering, Georgia Institute of Technology, to represent them in October 2012. Maracle and Ratliff selected Louis Martin Vega, Dean of the College of Engineering at North Carolina State University, as the panel chairperson in December 2012, and the panel commenced its work in January 2013. Work process. From January 2013 to June 2018, the panel worked with the USPS and the NRLCA to design and develop RRECS. Various development teams inside and outside USPS contributed to this process. The teams and their main contributions are as follows: USPS Engineering, select, test, and program electronic onboard recorder, MDD, test GPS capabilities, develop cloud computing capability, rural street database, develop software to map routes and capture street data, design and maintain database for storing street data, Solver, Accenture, manage cloud computing, street data analytics, GPS algorithms and data structuring, liaison with input data sources, MicroStrategy support, tracker, RWHT data capture, output analytics, data warehousing, payroll interface, standards, Institute of Industrial and Systems Engineering, IISE Solutions. 1. Develop engineered standards, validate input counts, operations, provide training for mapping and data capture, manage interface between RRECS and operations, provide operations support and knowledge for all teams, NRLCA, co-lead all functions of operations team, participate in all teams, manage input of union members and staff, provide labor relations support and knowledge for all teams and project management, coordinate activities of all teams, provide administrative support for panel and teams, lead project planning. Role of the panel. The main role of the panel was to establish the technical requirements for RRECS. They did this by circulating a series of documents to the teams, obtaining their feedback, and revising the requirements as necessary. Their role in the development process was to advise, monitor progress, and assess outcomes. The teams were responsible for the actual design and development of the various components of the system. The panel and its consultants played a primary role in testing and validating the systems developed by the teams. Scope of RRECS. RRECS covers all rural carrier work activities on all rural routes. It identifies the data elements required to count all work activities and creates a complex data capture system to provide daily counts of each of the data elements. RRECS also includes standards, carefully developed from engineering and statistical data, that specify the time allowed to complete each work activity. The standards and the counts come together in RRECS business logic that computes base hours for purposes of establishing evaluations of rural routes for pay purposes. RRECS is essential to the future of USPS. The necessity of a modern system of delivery route standards. USPS utilizes a base route structure to deliver mail to business and residential customers. The base is a fixed set of addresses that are specified in the Address Management System, AMS. While in the delivery unit, the carrier performs the activities, example, casing mail, sorting parcels and loading the delivery vehicle, necessary to prepare their route's mail for delivery. These office activities are similar in form each day, but may require substantially different amounts of time because of differences in mail stream volumes. The street activities on the route include driving, servicing mailboxes, and performing services at the customer's door, example, delivering large parcels. The line of travel should be the same each day, and the time required for this basic route approximately the same each day if 1. All customers on the route receive mail, 2. There are no door services for the day, and 3. There are no driving disruptions, example, detours. However, variability in the at-door services, particularly parcel delivery, often causes both the street time and the line of travel to vary from day to day. The concept of standard time for a delivery route refers to the time required by an experienced and motivated worker of normal skill and ability, working at a normal day work pace, to perform a specific task under specific conditions with allowance time to meet personal needs, overcome the fatiguing aspects of work and compensate for unavoidable delays. This concept is critical both for designing good routes and for managing the carriers who service these routes. Without a reliable method for estimating the time required to service a route, there is no way to know if the route's required activities can all be performed within an acceptable workday. Also, since for the street portion of the route, a carrier is out of sight of any supervisor, and no two routes are the same, it is not possible to evaluate the performance of a carrier without some concept of standard time. Basis for pay system. For rural routes, USPS uses standard route time to define the base hours used as the basis for carrier pay. The carrier is responsible for performing all required activities on his or her defined route. When these required activities are completed, the carrier's workday for USPS is finished regardless of the actual time required to complete the work. This use of delivery route standards requires sufficient precision for both USPS and the NRLCA to agree that the standard route time is fair to both USPS and the carriers. If the standard route time is fair, this concept for managing delivery systems has significant advantages for both parties. USPS is assured of getting a fair amount of work for a fair amount of pay with very little management required. The carriers are enabled to work at their own pace, and to get the benefit of working smarter and or faster by being allowed to end their workday when the defined work has been completed. The primary challenge is to have rigorous engineering processes and systems that generate fair standards and keeps them fair in a changing environment. A secondary challenge is to maintain sufficient rigor and transparency of these processes to continuously assure both parties that the standards are indeed fair. Constantly changing environment. Maintaining standard route times in the constantly changing USPS environment requires that the standard time calculations be based on current data. The existing USPS methodology for establishing standard times involves periodic manual counts of mail for each route during a representative period. However, given the variability in mail volume for the various streams, particularly parcels, it is extremely difficult to justify any period as representative of mail flows for the entire year. In order to adapt to the changing environment, standard time computations must be based on ongoing measurements of the various mail streams. The only practical way to accomplish this is with automated data capture of the actual mail streams over the entire evaluation period. Any methodology, such as the current manual mail count process, that creates static route standards based on limited data from a short time period will neither be accurate nor sustainable. Defining delivery route active ITIs. The methodology used here for developing standard times for delivery routes is based on the following guidelines. The pace required is that of an experienced and motivated worker of normal skill and ability, working at a normal day work pace. Each activity will be performed using a specified standard method. The standard methods will satisfy all USPS policies and safety requirements. The route can be reasonably approximated by a set of defined activities performed sequentially. No portion of any two defined activities are performed at the same time. The time required to perform a defined activity is approximately the same each time the activity is performed. The number of times an activity occurs can be counted. The standard time for the route will be calculated by summing, for all activities, the standard time for each activity multiplied by the number of times the activity is performed. Developing standard times. At a high level, the major steps in developing standard times for delivery routes are: 1. Define a set of activities, following the guidelines above, that include all work required to be performed on the route. 2. Define a standard method for each activity. 3. Determine the methodology to be used for developing the time standards. 4. Develop the time standards. 5. Validate the standards or modify as necessary. 6. Determine how to count the number of occurrences of all defined activities and 7. Validate the count system or modify as necessary. Engineered standards based on MTM, methods time management, analysis, have been developed and validated for most delivery route activities. However, a statistical approach was determined to be the best choice for drive time standards since drive speed is influenced more by the vehicle and distance driven than by the manual effort and skill of the carrier. MTM is not applicable in these circumstances. Furthermore, there is a large volume of statistical data available to establish the standards. Standards for traffic control points are also based on statistical data for similar reasons. Vehicle loading, end-of-shift activities, and deviations for express mail deliveries are all based on capturing actual time rather than on engineered or statistical standards. These activities vary greatly from route to route and from day to day on a given route, and thus neither MTM nor a statistical approach would work well. The data capture system. Introduction. RRECS is based on defining all work activities, counting the number of times each activity occurs, and calculating standard time for the activity by multiplying the count by the standard for a single occurrence of the activity. The two major inputs in RRECS are the counts and the standards. This section covers the data capture systems responsible for counts of mail volume, office and route characteristics, work activities, and other data elements necessary to calculate daily standard time. In total, RRECS includes 69 active data elements from a variety of sources, old and new, within USPS. The system is mostly automated, and it generates data daily that flows to solver and tracker, where it is combined with standards in calculating RRECS outputs. The RRECS data capture system replaces mail counts in the current evaluated compensation system, ECS. The mail count procedure involves manual counting of mail volumes by carriers and supervisors for a 2 or 4 week period. Mail counts are costly, disruptive, and sometimes perceived by carriers to be inaccurate and unfair. The mail count procedure assumes that mail volumes recorded during the mail count period will provide a reasonable prediction of volumes in the upcoming year or longer, and compensation based on mail count volumes will be fair and reasonable. In contrast, when it is fully operative, RRECS will base compensation on volume data collected over a 12-month period, thus capturing the full seasonal cycle of mail volume. The RRECS system will largely eliminate manual counting of mail. Automation of counting procedures under RRECS should greatly reduce data capture costs and improve quality of counts. When specifying the requirements of the data capture system, the panel relied on 4 guiding principles. First, all data capture systems should be digitized. Since we live in the digital age, this principle may seem self-evident. However, the panel soon discovered that some of the required data was only available in pencil and paper systems, while some, such as physical details of a route, existed only in the minds of USPS employees. Second, whenever possible, obtain the data from existing USPS data systems rather than create new data systems for RRECS. The panel discovered that many of the required data elements were already available somewhere within USPS, where they were being collected for purposes other than rural carrier compensation. In these situations, the task at hand was to identify, extract, transfer and reformat as necessary, so that the data element could be used in RRECS. Third, whenever possible, use automated rather than manual data collection. In the end, some RRECS data capture procedures are fully automated, some are semi-automated with minimal carrier input, and some required substantial carrier input with minimal automation. Fourth, when manual input is necessary, the cost of counting should be low relative to the cost of performing the work activity being counted. It makes no sense to have elaborate and costly systems to count activities that contribute relatively little to the overall route evaluation. RRECS data capture subsystems. Product Tracking and Reporting. Product Tracking and Reporting, PTR, is a pre-existing USPS database that stores tracking scan data for all barcode parcels and extra services products. Mobile delivery devices, MDD, are handheld scanners that rural carriers use in product tracking. The MDDs have GPS capability and hence record time and location latitude and longitude, LATLON, whenever a scan occurs. They also generate a stream of GPS coordinates at 1-second intervals, which provide a continuous record of the location of the device. The MDD can also capture data with programmable keys and touchscreen capability. To simplify the narrative, we will refer to all data captured by traditional scans and programmable keys/touchscreen entries as scan data or scans, and the continuous GPS data as breadcrumbs. PTR is the repository of scan data. RRECS discovered that some item scans used for product tracking were already available in PTR for parcels, accountable mail signature items, collect on delivery, COD. Mail and carrier pickup events and items. The accountable mail signature items and COD scans were usable, as is, in RRECS, and needed only to be extracted from PTR and transferred to Solver. Parcel scans required two modifications: 1. Introduction of a new scan to capture the small percent of parcels that lacked a readable barcode, some international parcels, damaged and missing barcodes, and 2. Modification of the scan procedure to capture the delivery location, door, mailbox, parcel locker. Carrier pickup also required modification to get complete and accurate counts. A new replacement scan that records each carrier pickup event and the number of items retrieved is required. RRECS data capture requirements also specify about 17 entirely new RRECS scans designed to count activities not previously counted, perform timekeeping functions, and capture actual time for 3 data elements: load vehicle, end-of-shift activities and deviation for express mail delivery. A total of 31 RRECS data elements are captured by scans in a semi-automated process. Rural carriers are responsible for making the scans at the proper times and locations. The remainder of the process of capturing, identifying, transferring, ingesting and analyzing the scans is fully automated. End-of-run reports. The Web End-of-Run (WebEOR) system is a pre-existing USPS reporting system that collects, stores and reports mail volume data based on processing machine-run reports. WebEOR data is available at the route level. It is used in RRECS for counts of DPS letters, DPS flats and second-run DPS letters. WebEOR data is fed directly to Tracker in a fully automated process. Informed visibility. 4 is a newly organized USPS real-time, single source for all mail and mail aggregate information, leveraging data to provide business intelligence for USPS functional groups and the mailing industry. RRECS uses 4 to develop counts of carrier routed. 11. Flats, CRF. 4 provides route-level data on full-service CRFs, which does not include non-full-service flats. At the national level, 4 reports totals for both full-service and total CRFs. The panel uses the national-level data to compute an inflation factor, total/full service, that is applied to route level, full-service totals to arrive at an estimate of total CRFs at the route level. The data capture process is fully automated. Rural Work Hour Tracker User Interface. Rural Work Hour Tracker, RWHT, is a relatively new USPS web application used to enter and track work hours for rural carriers. RRECS piggybacked onto RWHT, which was modified to contain 2 screens in its user interface, one to capture data elements required to calculate office walking distances, and a second to capture additional RRECS inputs. For office walking, the carrier and supervisor measure specified walking segments using a measuring wheel and enter the measurements in RWHT. Once entered, the distances need to be re-entered only if the office layout changes and walking patterns are altered. The second screen is used to record the withdrawal option for the route and the carrier's choice to case DPS letters or take them to the street. These data elements are only re-entered if they change. Rural Street Database. The Rural Street Database, RSD, was created for RRECS to map routes digitally and collect information about the physical characteristics of the route not available elsewhere. The RSD route mapping process starts with the collection of daily breadcrumbs from the MDD collected over a 4 to 6 week period just prior to mapping. Solver uses an algorithm to identify the locations of frequent stops from the pool of daily breadcrumbs. The frequent stops are displayed in the mapping software to aid the carrier in mapping the route. In the Delivery Point Manager process, DPM, the carrier starts at the delivery unit and proceeds to the first and each subsequent mail stop with the frequent stop locations serving as guides. The carrier also has available the addresses served on the route listed in delivery order, which DPM has obtained from the Address Management System, AMS. The carrier plots the locations of 4 points for each address: 1. The mail stop, vehicle park point for regular mail delivery; 2. The box, location where regular mail is delivered daily; 3. Direct door delivery, DDD, stop, vehicle park point for delivery of parcels and special service mail to the door; and 4. Door, location where customer receives parcel and special service mail deliveries. For each mail stop that serves multiple addresses, the carrier indicates which specific addresses are served at the mail stop. In the second step, the carrier utilizes the Line of Travel Manager program, LTM, to verify the line of travel and plot the locations of the traffic control points, stop signs, traffic lights, etc. The carrier then certifies the accuracy of the route mapping data. RSD mapping provides key inputs for several RRECS standard time calculations. Map distances between mail stops, TCP location and segment endpoints are used to define intervals for calculating drive time on the basic route. The locations of the mail stop, DDD stop and door are used to calculate out-of-route, OOR, driving distance, which yields OOR drive time when combined with the drive speed matrix. The DDD stop and door locations are also used to establish walk distance and walk time for door deliveries. RSD also has a data entry screen, which is used to capture details of dismount deliveries, such as the number of units, CBU, cent, NPU, active addresses, and collection compartments. These entries are used to calculate unit time, box time and collection compartment time, 3 key components of service time on the basic route. A fourth component of service time, dismount distance, is entered directly from the E4003, a digital database for PS Form 4003 data. RSD is important because it captures essential information about the route, such as stop locations, delivery locations, and delivery point characteristics, that were not previously available in electronic format. This information existed in carriers' minds and nowhere else. RSD data is used to calculate standard times that reflect the specific characteristics of a route. This is especially significant because this data is used to calculate the largest components of standard time, drive time and service time on the basic route. Route mapping and data entry are manual processes, the feeds and analytics are automated. Data collection exception handling. The panel estimated that about 1.3 billion data element entries will be required annually in RRECS. Some entries are fully automated, most are semi-automated, and a few involve manual data capture. Inevitably there will be missing and incorrect data due to system problems, technology failures, and human errors. Given the volume of data in RRECS, it is essential that these data exceptions be identified and controlled programmatically. With these ends in mind, RRECS contains logic and solver that identifies probable missing and anomalous data. Solver screens the input data, identifies exceptions, and sends the input file, with exceptions flagged, to Tracker. Tracker contains logic for handling exceptions, which generally involves inserting values, based on historical averages in place of the exceptions. Tracker also maintains a file that continuously updates the historical averages as new daily entries are made. Eventually, when a calendar year of data has accumulated, the historical averages will be computed as rolling averages based on adding the most recent day and dropping the oldest day in the annual cycle. The substitution of historical data for exceptions enables Tracker to compute standard times for all work activities that comprise daily standard time, thus maintaining the integrity of daily standard time calculations for each delivery day. This in turn means that the calculation of current weekly evaluations, CWE, which are computed from daily standard times, will be based on complete daily data. Substitutions based on average values are mathematically neutral in their impact on weekly evaluations. The standards, introduction. The role of standards within RRECS is to determine the amount of time allowed to perform a single occurrence of a standardized work activity. Technically, a standard is defined as the amount of time required by an experienced and motivated worker of normal skill and ability, working at a normal day work pace, to perform a specific task under specific conditions. A standard is composed of normal time, or the amount of time required to perform the work, and allowance time, or the time allowed for personal time, recovery from fatigue, and unavoidable delays, PFD. Normal time is determined through the systematic application of work measurement techniques. Allowance time is sometimes set by direct measurement, especially fatigue and delay times, but more commonly through administrative application of industrial engineering norms. RRECS establishes new standards for all rural carrier work activities that replace the standards in the current evaluated system. Many of the existing standards were negotiated, established through arbitration decisions, or developed by methods that do not conform to generally accepted industrial engineering practices. Indeed, much of the motivation to create RRECS arose from disputes between the parties over the accuracy of existing standards. Conflicts also occurred because of poor and incomplete documentation. In some cases, the parties disagreed over exactly which work activities were covered by a standard. It is very difficult to resolve disputes over the adequacy of time allowed to perform an activity if there is no agreement over the scope of the activity. These problems generated intense labor relations disputes and costly arbitrations. They also made it very difficult to manage change associated with introduction of new technology, new products and services, and innovations in work process. RRECS addresses these problems by developing new standards based on the systematic application of industrial engineering techniques. The RRECS standards are transparent in that the coverage of each standard is clearly defined, and the step-by-step work measurement process for developing normal time is fully documented. RRECS has three categories of standards: engineered standards, statistical standards, and standards based on actual time. In total, RRECS includes 122 standards. The most important category is engineering standards, accounting for 112 of the total. RRECS engineered standards were developed using the predetermined motion time system, methods time management, MTM, which is a widely recognized work measurement technique within industrial engineering. MTM was developed and is maintained by the MTM Association. Briefly, in MTM1, the original MTM system, normal time is developed by describing the work activities with a standard set of micro-motion symbols and assigning a predetermined time to each motion. Since MTM times are normal times, allowance time must be added to arrive at standard time. RRECS statistical standards cover two work activities: driving and stopping at traffic control points. These standards were developed by collecting actual times for driving and stopping on a representative group of rural routes over a representative time period. The actual times were calculated from GPS breadcrumbs corresponding with the start and ending points of the activity. Each activity had thousands of observations from which mean driving and stop times were calculated. Drive time standards include a delay allowance of 3.41%, which was based on a driving delay study, and a 3.23% personal allowance, totaling 6.46%. In effect, this methodology is based on the premise that mean driving speeds on a large representative sample of rural routes is a reasonable approximation of normal times for driving. The panel used statistical methods for drive time and TCP stop time because normal times for these activities could not be determined by work measurement procedures like MTM, which are designed for manual work, where pace is controlled by the worker. Stop times for traffic control points include a personal allowance of 3.23%. No time was allowed for delays, since the activities being measured are stops. The final category, RRECS standards based on actual time, cover four work activities: loading mail in the vehicle, end-of-shift activities, deviations for express mail deliveries, and time for safety and service talks. As in the case of statistical standards, this category is based on the collection of actual times. However, in this case, the actual times are route-specific and based on ongoing data collection. Actual times for each occurrence are calculated daily from scans at the start and end of the activity. The time allowed for the activity in the route evaluation is the average of the daily times over a representative period. Since the actual times for these activities cover both work time, normal time, and interruptions for both fatigue and unavoidable delays, the only allowance time added to them is the 3.23% for personal time. In the case of end-of-shift time, personal time is deleted because it is likely to occur in the form of a short break included in actual elapsed time. The panel chose to base the standards for these activities on actual time because of the great variation in work content due to vehicle characteristics, mil volumes, activities performed, etc., that made it impossible to develop a standard method and engineered standards for the activities. Significant inter-route variation in the activities rule out the statistical standard approach. In deciding on the proper standard setting approach for each work activity, the panel followed three important principles. Whenever possible, develop an engineered standard. When setting statistical standards, base the standard on a representative sample of routes, a representative time period, and a large number of observations. Use direct measurement of actual time only when the work activity is deemed to be unmeasurable using engineered or statistical methods. Two additional principles also guided the panel's standard setting actions. First, all methods and results should be transparent and documented in enough detail, so the parties could understand exactly how the standard was developed, and the methodology could be replicated. Second, all standards should be validated. The remainder of this section elaborates on how these principles were applied in the development of RRECS standards. A detailed spreadsheet with explanations of each standard and a comparison to current standards can be found here. Developing, documenting, validating, and maintaining engineered standards. Developing engineered standards. Clearly define the work activity covered by each standard. The content of each activity was determined by a. Direct observation of rural carriers performing the work, b. Consulting USPS standard operating procedures, the labor agreement, and other relevant documents, and c. Interviewing rural carriers, postal managers, and other subject matter experts. Determine the starting and ending point of each work activity. To avoid double counting, the work activities must be mutually exclusive. In aggregate, the work activities should cover all the work performed by rural carriers. Establish a standard method for performing the work activity and use it to develop the standard. The work activity is divided into a series of work elements, each with a discrete starting and ending point. The elements are then arranged into an efficient and safe method that can be mastered by an experienced and motivated worker of normal skill and ability. The standard method is written in plain English and presented in a standard format and writing style. The standard method is important for three reasons. First, it serves as the blueprint on which the engineered standard is based. Second, it serves as a record of work content at the time the standard was set, and as such, is available as a reference point to determine if the work has evolved in response to changes in materials, equipment, layout, product changes, etc. that may require a revision of the method and standard. Third, the standard method is available for training new carriers and retraining experienced carriers. It is important to note that the standard method is not the only way the work can be satisfactorily performed. This is especially true in long-cycled, varied work performed in varied conditions and circumstances, as is the case with rural mail delivery. Under these conditions, the standard method should be a representative way of performing the activity and a reasonable basis for establishing the standard. Apply MTM work measurement techniques to the standard method of each work activity. Each element of the work activity is broken down into micromotions using the standard MTM motion categories: reach, grasp, move, position, apply pressure, release, etc., and the specifics of each micromotion are specified. The micromotion analysis for an element is presented in standard MTM detail sheets that record, in sequence, the MTM symbols for micromotions performed by each hand, the normal time values corresponding with each micromotion, and a brief plain English description of the work. Construct normal times for work activities using application spreadsheets that reference the MTM detail sheets. The detail sheet results are aggregated in spreadsheets developed by the engineer. Typically, the elements are listed in the spreadsheet in the order they are. 15. Performed. Each row of the spreadsheet corresponds with a constituent work element that is part of the overall activity. The columns of the spreadsheet provide a plain English description of the work element, the reference number for the detail sheet of the element, the elemental normal time from the detail sheet, and the frequency, if it is greater than or less than 1. The elemental times adjusted by frequency are summed to arrive at the normal time for the work activity as a whole. The spreadsheets constitute a kind of roadmap for organizing and presenting the detail sheets used in the calculation of activity normal time. Add allowance time for personal fatigue and delays, PFD, to arrive at standard time for the work activity. A PFD allowance of 10.23% was applied by multiplying normal time by 110.23% to calculate the standard. Validating engineered standards. Independent review. All activity normal times were validated in a process in which the panel independently reviewed the standard method, application spreadsheets and MTM detailed sheets and compared its results with those obtained by IISE. The purposes of this review were twofold: to verify that the standard method was efficient, safe, and attainable with reasonable training and effort, and to assess whether MTM methodology had been properly applied in developing normal times based on the standard method. All differences between IISE and the panel were discussed and resolved by consensus. Statistical review. The second level of validation involved comparing standard and normal times with actual times collected on a sample of representative routes during a representative time period for large group of carriers. Since time data was collected passively without direct intervention by IISE or any other group, it is very likely that the carriers used the same methods, including shortcuts, and worked at the same pace they normally do under the current evaluated compensation system, ECS. Under these circumstances, one would expect the gap between actual time and standard time to be relatively large, since the recent average level of performance in the ECS is around 113 to 117%. The second approach for capturing actual time data is based on GPS breadcrumb data. RRECS contains algorithms that identify the time that a vehicle stops and the time that it starts again from the GPS breadcrumb data generated by the MDD. This means that actual time data can be generated for mail stops for delivering mail to the mailbox, and for stops to make door deliveries, DDD stops. This method for capturing actual times is automated, and as such requires no intervention by the carrier. It is virtually costless and free of observational bias. Under RRECS, mail stops are classified by delivery type, curb, other, sidewalk, CBU, sent, etc., in the Rural Street Database, RSD, and thus the delivery classification of the stop tells us what work activities will occur at the stop. Work activities during the mail stop differ substantially by delivery type. For example, curb stops are simple and are composed of one standard box time. There is variation in the curb box times based on whether the delivery mode is 1-, 2-, or 3 bundle, and this designation can easily be determined from a simple lookup matrix. For example, the statistical data for mail stops for curb deliveries can easily be sorted by bundle type, and the separate standards can be validated against the appropriate grouping of actual times. By contrast, a mail stop to service a CBU includes 5 separate work activities: dismount and prep, gather mail for delivery, walk to the CBU and return, unit time associated with opening and closing the door of each separate CBU serviced at the stop, and box time at each address. Statistical review can also be used to validate standards for work activities at DDD stops. As in the case of the mail stops, the actual DDD 16 stop time is calculated from GPS breadcrumb data corresponding with the start point and end point of the stop. The activities performed at the stop are determined by an algorithm that associates activity scans with specific DDD stops, e.g. deliver parcel to door or deliver accountable mail, signature item. Once we know the purpose of the trip to the door from the scan, it is easy to identify the work activities associated with the trip. For example, delivery of a parcel to the door requires the following activities: gather the item to be delivered, dismount and prep vehicle, walk to and from the door, and service time at the door. The standard times for these activities can then be compared to the actual time for the stop. Sometimes more than one type of delivery and/or pickup occurs on a single trip, and sometimes more than one item of the same type is delivered or picked up, but usually trips have a single purpose, such as deliver one parcel. This means that it is easy to use data filters to zero in on the simplest cases, and get clean clusters of work activities for comparing the actual time with the sum of the component standard times. This approach was used to validate 6 standards: deliver large parcels, deliver accountable mail, signature items, deliver collect on delivery item, collect customs due, collect postage due, and pick up prepaid item. Time study review. The third level of validation compares the actual time required to perform the activity with the normal and standard times developed by IISE and reviewed by the panel. The purpose of this validation was to determine how well carriers trained in the standard method would perform against normal and standard times. It is a rough validation in that carrier performance will also reflect the work pace of the carrier. Nevertheless, these comparisons are frequently made, and they provide a reasonable basis for validating new standards. The third level of validation focused on the most important standards in terms of their contribution to route evaluations. The steps involved in time study validation process were as follows. The IISE team reviewed the standard method with the carrier and responded to any questions the carrier had regarding the method. IISE determined, in advance of the work being performed, the number of times the activity would be performed. This was accomplished by counting the number of mail pieces in per piece standards, addresses in per address standards, etc. IISE timed the carrier performing all iterations of the work activity. IISE calculated average actual time per occurrence, per piece, per address, etc., by dividing total time for all occurrences by the number of occurrences. IISE compared average observed time with normal time and standard time for the activity. We provide both comparisons because the actual time for the activities contains some very short delays and small quantities of personal and fatigue time. By contrast, normal time contains no PFD time, hence normal time is not the perfect match for comparative purposes. On the other hand, the amount of PFD time actually occurring during these studies is unlikely to be equivalent to the allowance factor, because carriers are unlikely to stop for personal or fatigue time while being observed during the study. Hence standard time is also not the perfect match, because actual time is unlikely to include the full complement of PFD time. By and large, the time study validation results indicate that carrier performance against normal and standard times falls in the expected range. This indicates that the standards provide a fair amount of time to do the work, when carriers follow the standard method. Developing and documenting statistical standards. GPS data capture. The tracking of carriers as they service their routes. There are inherent problems that must be addressed in using GPS technology. Current mobile devices for capturing breadcrumbs are reasonably accurate when the GPS satellites are not blocked. However, the signal is typically very distorted when a device is taken inside a building, and there is always some random error in the coordinates, even when signals have a clear path from satellite to device. A second problem arises in identifying stops. When a device is actually stopped, the error in GPS capture sometimes makes it appear as if it is still moving. RRECS uses algorithms and the pooled data to estimate when the device speed falls below a specified threshold, about walking speed, and defines this as a stop. Again, the pooled data minimizes the impact of random errors and increases the accuracy of stop times. The data capture system works as follows. The MDD is the portable device used by carriers to scan parcels and input other data via menus on the device. The MDD generates GPS coordinates at a rate of 1 per second and can transmit these coordinates to the Amazon cloud. Developing statistical standards. RRECS has two groups of statistical standards: drive speeds and traffic control points. Both are based on statistical analysis of elapsed times calculated from GPS breadcrumb data. However, the procedures and outcomes differ, so they will be described separately below. Drive speed standards. The basic premise of the drive speed standards is that drive speed is governed primarily by the length of the distance driven from one full stop to the next full stop. With this as an organizing principle, drive speed standards are calculated as follows. An interval is defined as the distance in feet from one mail stop, traffic control point or segment endpoint to the next mail stop, traffic control point or segment endpoint. Mapped stops is defined as a valid interval if the daily breadcrumb path indicates a stop at both locations, and no unidentified stops occur between them. RRECS calculates the distance in feet between the stops that define the interval from the lat-long data in RSD for the mapped location of the 2 points. Travel time in decimal minutes for the valid interval is calculated from the breadcrumb that defines the end point of the first stop to the breadcrumb that defines the start point of the second stop. At this point, RRECS has distance and time for each valid interval and can calculate speed in minutes per foot. The last step is to sort interval speeds into predetermined distance ranges based on their mapped distances. The distance ranges are organized into a drive speed matrix, DSM, in ascending order, and the mean drive speed for each distance range is calculated from the data points sorted to it. This process was used to develop a drive speed matrix, DSM, in RRECS consisting of 47 distance ranges. The DSM is based on data collected for almost 24 million intervals during the calendar year from August 1, 2016 to July 31, 2017. The panel also ran the analysis for each month of the year to see if there was significant month-to-month variation in driving speeds. The data indicate that variations in monthly speed are minimal, so the final DSM is based on the annual data and applies to all rural routes. Unavoidable delays in driving. During a normal workday, carriers encounter a variety of unavoidable delays while driving. These include stops when making three-point turns, entering traffic, being delayed in traffic, and encountering miscellaneous obstacles in the line of travel. None of these unavoidable delays are accounted for in the drive speed matrix. The drive speed study specifically eliminated any intervals with unidentified stops between interval endpoints, hence, the unavoidable delays are not reflected in lower drive speeds. Consequently, to determine the amount of allowance time that should be added to drive time to cover unavoidable delays, the study involved projecting the RSD address and mail stop locations and the solver MDD breadcrumb trails on Google Earth Maps. A simple system was used to identify the most likely cause of each of the breadcrumb stops not matched to mail delivery stops. A team of Georgia Tech students, under the supervision of panel experts, examined a representative random sample of 179 routes using this methodology. Analysis of the output from this study resulted in an estimate of 3.41% for unavoidable delays while driving. As a result, the entries for standard drive times in the matrix include a 3.41% allowance for unavoidable delays. 2. TCP standards. TCP standards are based on 1. The vehicle stop time at the TCP measured from GPS breadcrumb data, and 2. The frequency that the vehicle stops, calculated by dividing the number of actual stops by the number of eligible stops. The data used in developing TCP standards was collected during the same 12-month period as the DSM data. Sample sizes ranged from about 1.5 million in the case of stop signs to several thousand in the case of access gates. Direct measurement of actual time. The 4 work activities that are measured by actual time at the route level are load vehicle, end-of-shift activities, express mail deviations and time for safety and service talks. The basic procedure for capturing times for these activities is the same. The carrier signals the start of the activity on the MDD just before performing the work, and the end of the activity just after completing the work. The start and end points must be clearly defined, and the carrier must be trained to recognize them and correctly perform the data capture procedures. RRECS measures the actual time for these activities because, in each case, engineered standards were not a practical solution. The engineered standards approach requires the calculation of standard time and the ability to develop a standard method for each activity. In the case of load vehicle, this approach is impractical because the great diversity among routes and vehicle characteristics, mail mix, and mail volume means defining a single standard method is not possible. Consequently, the engineered standards approach would require separate standards for subgroups defined to produce greater internal uniformity. Not only would it be very difficult to specify the defining characteristics of such subgroups, if they could be created, each would require to its own standard and separate counts of its own unique data elements. The engineered standards approach in this context would be expensive to develop, operate, and maintain. This point is implicitly recognized in current evaluated system, in which load vehicle time is also based on the direct measurement of actual time, albeit during a mail count period. The end of shift period is also very difficult to measure. Many possible activities can occur in the office at the end of the day. Different activities are performed on different routes, and different activities are performed on the same route on different days. Once again, the panel concluded that it would be impractical and expensive to develop engineered standards and data capture procedures for the many short activities performed during this period. Deviation for express mail delivery is a relatively rare event. Many express mail deliveries are fully integrated with regular mail delivery and do not require any deviation from the basic route and normal direct door deliveries. When deviation is required, there is no set procedure governing how it occurs. That is, no standardization of where the carrier departs from and returns to the basic route, and no uniformity in whether the deviation is made on foot or by a combination of driving and walking. Capturing and assigning time to irregular travel patterns of this sort is extremely difficult with GPS technology. Given the great difficulty of using the engineered standards in this context, and the relatively small contribution the activity makes to the overall route evaluation, the panel opted for direct measurement of actual time. 19. Route coverage. The concept of route coverage is used to estimate the addresses actually serviced each day on each delivery route in order to give the carrier credit for the actual work performed. Current USPS standards are based on the number of addresses eligible for service rather than on those actually served. Since the RRECS standards are based on a standard time for each address served, using the number of eligible addresses would overestimate the actual work required. The parties are still in discussion and development of a coverage factor calculation using both breadcrumb data and information from informed delivery databases to determine how many eligible boxes were served on any given day. The parties have already agreed that, on any day the route is credited with a box holder or walk sequenced mailing, the route coverage for that day will be defaulted to 100%. Calculating and updating base hours and evaluated hours. Background on base hours, BH, and evaluated hours, EH. BH represents the weekly standard hours and minutes for 6 delivery days on a route. BH in combination with the route classification, HJK, translates in each pay period into EH, which determines the carrier's pay. Hence BH drives carrier's pay, and is the ultimate output of RRECS. This section covers the methodology for calculating, updating and recalculating BH. Under new procedures currently in development, Tracker will inherit responsibility from payroll and EGAN for determining EH. Business logic for base hours. Before a route can transition from the current evaluated compensation system, ECS, to RRECS, several steps must be followed. First, 4 to 6 weeks of breadcrumbs must be accumulated on the route, so Solver can create a file that identifies the frequent stops. Second, the carrier must map the route and enter route data in RSD. Third, values of data elements for the route must accumulate for a long enough period of time to generate a reasonable interim evaluation of the route. Fourth, Tracker and Solver must calculate evaluations in the automated RRECS system. Fifth, when the first interim period is over, Tracker must calculate BH for the initial evaluation of the route. Sixth, Tracker must repeat the previous step for each subsequent interim period during the phase-in year. Last, Tracker must have automated procedures in place to update the route in each pay period if triggering events for an update occur, and to create a new evaluation of the route if triggering events for a new evaluation occur. The initial determination of BH is simple. BH equals the most recent value of current weekly evaluation, CWE. RRECS calculates the CWE by computing the daily standard times and rolling these into a 6-day, weekly evaluation on a continuous basis. The Tracker logic selects the latest value of CWE, and it becomes the BH value used to determine the initial value of EH. The initial evaluation occurs when the route is mapped, certified and first enters RRECS. After the route is initially evaluated in this way, it becomes eligible for updates in each subsequent pay period based on changes in BH. In the subsequent pay periods, BH equals CWE plus AF, where CWE is the latest value available, and AF is an adjustment factor. Tracker stores current values of both BH and AF. CWE is an automated calculation that is available daily. The adjustment factor, AF, is necessary because the route is not remapped each time a small change occurs. The reasons are obvious. Mapping requires substantial time to accumulate breadcrumbs and complete the mapping process, and it is very expensive. Since small route changes do not result in remapping, an alternative procedure is necessary to estimate their impact and adjust the evaluation accordingly. This estimation procedure is exactly analogous to the process in the ECS that is used to update route evaluations between mail counts. AF is recalculated if a change in any of the following route characteristics occurs: route miles, regular boxes, central boxes, dismounts, dismount distances, interunit mail, low volume, interunit mail, high volume, collection points, blue box, or collection compartments. If the triggering event is a change in regular boxes or centralized boxes, a 10th calculation, for volume change associated with change in the number of addresses, is also made. The volume adjustment is based on volume factor calculated for each route by summing all volume-related sequences and dividing the resulting standard time by the number of addresses. The volume adjustment is calculated by multiplying the change in the number of addresses by the route volume factor. In each period in which a change in one or more of the 10 factors occurs, Tracker calculates the AF incremental change equal to the net change resulting from the sum of the 10 calculations. AF incremental changes are calculated for each pay period based on any changes in the 10 factors reported in the previous pay period. The AF is equal to the sum of all the AF incremental changes since the last RSD update. The AF and CWE are used to calculate bank time, BT. The parties will negotiate the frequency of base hour resets or adjustments to route evaluations and the events that may trigger the need for these changes/updates. Calculating base hours on new auxiliary routes after route adjustment. Background adjusted routes. Local managers need a simple procedure to estimate base hours on newly created auxiliary routes after route adjustments. In the discussion that follows, we will refer to the new auxiliary route that is created as the AUX route, and the existing adjusted route or routes as donor routes. Carriers on both the AUX and donor routes must be paid immediately after the adjustment. While RRECS procedures for new routes can produce interim evaluations after 13 weeks of data collection, they do not include a procedure for setting evaluations for the first 13 weeks after adjustment. This section of the report describes the automated procedure that will be used during this initial 13-week period. Business logic adjusted routes. The donor route contributes time to the AUX for the following 10 transfers: route miles, regular boxes, central boxes, dismounts, dismount distances, inter-unit mail, low volume, inter-unit mail, high volume, collection points, blue box, collection compartments, and mail volume. These are the same 10 items used to adjust base time and interim adjustments. The postmaster enters the amount of the transfer for 8 of the 10 items, excluding route miles and mail volume, and the business logic calculates the time transferred to the AUX route. For route miles, the postmaster must enter 3 pieces of information: the pre-transfer mileage and the drive time, basic route, for the donor route, and the miles transferred from the donor to the AUX route. The business logic calculates the standard time for the transferred miles from these 3 data points. For mail volume, the postmaster enters the volume factor of the donor route, and the business logic calculates the standard time for the mail volume transferred from the donor to the AUX route. The process is repeated for each donor route. The total time from the 10 calculations represents the time by which the donor base hours are reduced. The total time for the new auxiliary route is equal to sum of the time transferred from each donor route plus the time for fixed time activities, actual time activities, additional miles on the auxiliary route, and office walking. To determine fixed time, the postmaster must enter the withdrawal option and the vehicle type on the AUX route. The business logic selects the appropriate fixed time for the combination entered. Actual times on the AUX route are based on average times for load vehicle and end-of-shift activities. No entries are necessary. Additional miles are the stem and connecting segments that link transferred miles to the delivery unit and each other. The postmaster must estimate these miles, Google Map, driving, and enter the total additional miles. Finally, office walking requires the carrier and supervisor to take the actual measurements for the new auxiliary route. The business logic calculates total standard minutes for the AUX route by adding transferred, fixed, actual, additional miles and office walking minutes. The logic automatically calculates base hours for the new auxiliary route. The route adjustment process requires the postmaster to enter 12 pieces of information for each donor route and 3 pieces of information for the new auxiliary route. All calculations are automated. The output shows the base hour deductions from each donor route and the base hours for the auxiliary route. Conclusion. In this lengthy explanation, we have tried to condense the entire engineering panel report and focus on the factors that affect route evaluations, how those factors came to be, and how they will be managed in the future. In the next section, we will use some real-life examples to explain how RRECS will actually be used to calculate and maintain our route evaluations.